I'm Kurt Koitzer, and it's my pleasure to chair this session with our keynote addresses. In these keynote addresses, we try to really present to you the very cutting edge, the state of the art in research at the edge. Our first speaker is Diana MARCULESCU. She's a professor and holder of the Motorola Regents Chair in Electrical and Computer Engineering at the University of Texas at Austin. Her research interests include energy and reliability-aware computing, hardware-aware machine learning, computing for sustainability and natural science applications. And Diana received the National Science Foundation Faculty Career Award from years 2000 to 2004. She has won multiple Best Paper Awards and has served as the chair of several conferences and symposia in her area. Diana is also a fellow of the ACM and IEEE. And I've had the pleasure of seeing her presentation. You haven't, but I think you're really going to enjoy it. And I'm going to steal that title someday.
Thank you so much. Thank you so much, Kurt. It's an honor and a privilege to be here. I have to say I've just looked at this award session, and I have never had a real job. I've always been an academic, but my students all have real jobs and are working at great companies. So anyway, so the title of my talk that Kurt wants to steal is miliJoules for 1,000 Inferences. Machine learning systems on chip, but I corrected it, and I'm going to tell you how we can do it really cheaply. And I usually start with let's see how I can make this work. Yeah, with a very simple example. If you have your smartphone unconnected to the network and you have your you ask it, or your smart watch, you ask very simple questions. What is 100 divided by 2? What is my name? You know my name. Or what is Apple, the company? Typically, you'll get something of an answer that it's really not satisfying. And the reason for that is all these services are actually running the cloud. It's not because they wouldn't be able to run on these devices, or maybe it is because the models are perhaps too large, but also because this capability currently is running the cloud, but our goal and the goal of this summit is to actually look how we can push everything to the edge of the cloud, so on the devices that we currently use and we have around us. I don't have to tell you that machine learning, and in particular deep learning applications and models, are pushing all of these devices to the limit in all segments of the market, in automotive, in smart home, mobile wearables, virtual augmented reality. But one of the things, or many of the things that are there to stop us, come from the hardware. The hardware constraints are the key limiting factor for pushing all of these to edge. And one of the things that actually I'm concerned quite a bit with is energy or power consumption. And this is ancient data in machine learning times, 2017. But object detection run on a smartphone would drain the battery in 1 hour. And I'm sure now with larger models, even with better devices, that's still valid. We also have the challenge of having the edge to cloud communication constraints and the response time constraints that actually are very important to the user. So when we look at the spectrum of what we can achieve within a certain power or storage constraint, with the current platforms, you can see here we might be using full precision, arithmetic with a large storage. But if we try to make these models tinier and smaller, we could try to perhaps implement all these arithmetic logic functions using purely logic operation and attempt to put everything in a smaller memory footprint. And you might think we can put this using or implement this using lightweight neural networks. We call them LightNNs, with bridging this gap between full precision and what we would have here, binarized neural networks, which I'm going to also talk about. The good news is that you can get orders of magnitude better energy, less area, with minimal loss in accuracy. And this appears to be a better solution than just assuming that your weights can be represented with just a binarized representation. So this is where binarized neural networks might be larger test or inference error, but quite a bit reduction in power and storage. Another approach to perhaps consider is to push these lightweight implementations to what we call LightNNs or flexible lightweight neural networks, in which we don't constrain the weights to be on a certain quantized level, but we allow a mix and match, so mixed precision kind of approach. And that actually is likely to improve accuracy without so much of a loss in power savings. There's also approaches that allow us to reduce the gap in accuracy here by doing this training of binarized neural networks better. So I'm going to tell you how we can achieve this. A little bit in terms of quantized neural networks, the very basic idea, which I'm sure you all know, is to replace multiply accumulate operations with a limited number of shift and add operations. So in our work, we really try to move away from the full-blown representation of weights to just constrain the weights to be a limited number, a limited sum of powers of 2. When we constrain this k or the number of powers of 2 to 1, then the equivalent multiply operation is just a shift. For 2, you just reduce it to 2 shifts and 1 add. And this is an explanation as to how this is done. So this is your original MAC, and this is how it turns into for LightNN for k equal to LightNN 2 implementation. Now, this requires a little bit of difference into how training is done. So typically in the 4-pass, we do this rounding. So this is where the weights are actually quantized into LightNN k representation, but then backprop still uses floating point gradients as well as the update weights is done the same classic way. The good news about this is that if you look at a comparison between conventional representations, the binary net and binary connect, which are the binarized representations using either only weights or both weights and activations as in binarized form, it fills this missing gap in terms of loss in accuracy. So if you look at the binarized representations compared to conventional ones, from 21%, it goes up to 43 to 73%, but the LightNN representations, they are able to fill this gap. So this is all great news. Furthermore, it can provide quite a bit of cheaper storage. So if you look at conventional versus LightNN 1, it's about an order of magnitude savings in storage and pretty comparable with the binarized versions. But what's more interesting is that you can get 2 orders of magnitude energy reduction without much accuracy loss. So what we have here is for 2 simple examples, MNIST and stWhat 10 datasets, and these results have been reproduced also for larger datasets like ImageNet. The LightNNs, which are in red, fill in the Pareto front, meaning the best accuracy model that you can get for a given energy constraint. Compared to, the blues are the conventional models. So LightNNs allow designers a wider range of identifying which configurations are best for your perhaps energy constraint and target test or inference error. The triangles indicate Pareto optimal configurations, which as you can see are more for the reds rather than the blues. So this is all good news. But when you look at filling this gap or pushing this envelope further towards lower inference error and better power efficiency, then we think about, can we do it better? Do we need to restrict the way we quantize our weights to just 1 or 2 powers of 2? Can we mix and match? And the answer to that is yes. We can learn whether we want to use filters represented using just LightNN 1 or LightNN 2. So this is assuming that everything is representing as a power of 2. This is 2 powers of 2, combinations of 2 powers of 2. But perhaps during training, we can learn which of these filters should be represented using LightNN 1 versus LightNN 2. So during training, we identify which is best, and we mix and match. And unsurprisingly, this is good news because it does offer the LightNN representation, which is in green here, achieves better accuracy for a given storage constraint. So better than LightNN 1, which is the red, and better than LightNN 2, which is the blue. It's a little bit counterintuitive in the sense that you're mixing both and you're getting better results compared to either. But it all comes from the fact that training, you learn this, which weights are better represented with one versus the other. So everything, the winning strategy comes in the training. Of course, a mixed quantization or mixed precision raises challenges from both hardware and software. So we're going to see how we can solve that later. But talking about binarized neural networks, which are still here, you lose quite a bit of accuracy. The question that we also asked was, can we actually push it back? Can we bridge this gap that we still have here while still maintaining the advantages of low power and low storage? And the answer to that is yes, by identifying what exactly are the challenges in binarized neural networks or in training them. So typically in binarized neural networks, we represent the weights as just using 1 bit plus minus 1 representation, so basically using the sign bit. And this is a very cheap representation. If you do it for both bits and activations, this is quite cheap compared to LightNN 1, which still uses 4 bits, because remember, we need to identify which power of 2 do we need, and also we need to represent this using an according number of bits. If you look at how cheap this is very cheap compared to an actual multiply accumulate operation. And also not just in terms of energy, but also in terms of relative area. So quite a bit of savings there. So if you replace many of these expensive MAC operations with just XNORs and potentially some counters, then you can get quite an inexpensive, cheap replacement for these MAC operations. But it comes at an expense, and that expense is accuracy. And the accuracy drop usually comes from difficulties in training. And typically, when you have a binarized conv layer followed by batch norm, and then here you have your activations in hard 10H. Some of the pre-activation distribution issues that you might see are degeneration. So instead of having a really nice centered around 0 distribution, it's actually shifted to the left or right. Saturation is really not, it's pushing the standard deviation of the weight distribution outside of -1, 1, and the gradient mismatch basically makes for a very narrow distribution. So all of these create issues and actually impact accuracy, so drop, the resulting in accuracy drop. So to fix this, what we propose is to actually regularize the activation distribution to remove the chance that these issues show up. So these are the 3 typical things that the degeneration, saturation, and gradient mismatch. So we adjust the regularization such that the distribution is shifted to the 25th to 75th percentile. And of course, this has to be done such that this is differentiable. So this is regularization comes into the picture, and we do this during training, of course, in the regular SGD loop. And this is, again, recovering much of the accuracy loss. This is the baseline accuracy for some of the existing binarized neural network implementations. And it recovers, in some cases, up to 7% accuracy, which is really good. So when you put everything together, you can see that we're able to get a better trade-off in terms of power and accuracy. The question is this acceptable for your application? So in the case of binarized neural networks, they do come at a great storage benefit, but come at a cost of reduced accuracy. So many times when we discuss this with our industrial partners, the accuracy loss coming from a binarized neural implementation may not be acceptable. Therefore, lightweight or quantized neural networks can provide a better energy accuracy trade-off, but they may need hardware software support, especially if we rely on mixed precision. Can the platform provide it? Because you're going to need to support the different quantization levels, and also your software has to be written accordingly, and your mapping. Finally, both binarized and quantized neural networks are amenable to fast or low power implementation with computing memory technology. But we all know that computing memory typically relies on analog implementation, which introduces additional accuracy loss. Is that acceptable for your application? So these are all factors that you might want to consider in moving into implementing your neural networks with a smaller footprint by using either binarized or quantized representations. On top of it, or I should say, orthogonal to it is the idea of filter or channel pruning. And the basic idea here is that typically in your neural network where you do classification, this is a very simple example of image classification, you're pruning channels or filters, and as a result, you reduce computation and storage. But the downside is that accuracy can be hurt. So what looks like a tiny cute cat becomes a dog. So you need to fine tune, and that's extra effort to recover the loss in accuracy. And because of this fine tuning and the extra effort in redesigning the network after pruning, we need to think about what are the trade-offs in the computation resources that we need to recover that accuracy loss. So if you think in terms of the trade-off between computation or flops and accuracy, typically depending on the platform, so this might be something that is more amenable to slight pruning, but for something that's tinier, you might want to prune even further. What it would be great to do is to already have this trade-off curve and the models amenable to be implemented at various computation flop constraints, but know how much accuracy you're going to drop, because what you want to do is actually have this trade-off curve there for your model. You should know how good is this, what is the best that you can do. So ideally, this should be a Pareto curve. But also you want to do this fast, so you don't want to try over and over all these configurations. So ideally, it would be great to find this in one shot and then have a simple measure that tells you, okay, this model is going to land somewhere on this curve, but I don't have to refine it or tune it later. This is actually very important, especially in embodied AI applications, where both efficiency in performance as well as energy and form factor are important. So this is an example we have here, a very simple example. Time to destination, closeness to destination is important. So the way we envision this to make it in a cheaper fashion is to break this loop in typical pruning. Typically you prune, you check, and then you prune again until you're satisfied. And then this evaluation is what you care about, you as a user, right? But pruning is typically pretty expensive, and it has to be done over and over again until you get to your target. So ideally, what it would be great to do is do this once, and you get not just one, but multiple convnets with different complexities, and you can quickly say which of these convnets actually fits the target application for you. And you may have a different range of applications, and once you do this for a given model, then you can use it for various constraints that you may put on your application. The idea is actually pretty simple. We want to learn a global ranking of importance for filters, such that when given a certain computational budget, for example, flop count, we can do this pruning very simply with thresholding. So for example, if we rank these filters magically from lowest to highest importance, and we say, okay, if I'm going to prune the lowest 20% lowest filters, I get one model, or if I prune even more, then I get another one. But we need a way to match this importance to resulting impact in both accuracy as well as storage. Unfortunately, learning the right ranking or the optimal ranking is hard, and the complexity, I don't have to tell you, is really high. But making an assumption, relying on empirical results, I'm going to spare you the details, but the idea is that we have a transformation, a layer-wise transformation that allows us to use the L2 norms of the filter weight, so how large they are, and in some sort of metric that tells us how important they are. And we learn this. So by assuming an arbitrary percent flop or percent complexity, computation complexity of the original model, then we learn what this alpha and k might be, such that it maps this percentage of, or this importance maps to a given percentage of savings here in terms of complexity. And because we do this, we learned this, ideally it would be very close to the optimal. So it would be on the Pareto curve of the trade-off between complexity and accuracy. We call this ledger. So global ranking, we dub it as a ledger, and ledger is, as you can see, recovering quite a bit of the accuracy loss during pruning. So it's state of the art, or it was state of the art when we published it. It's hard to keep track these days. So for any type of network that we've tried, it was able to provide state-of-the-art accuracy at also very low flop count. So for a given flop count constraint, is able to determine the set of networks that are able to satisfy that constraint. So now, if you think of the two,
You think, Diana?
Yeah.
Diana, could you? I'm not catching the benchmarks that you're running. Of course, we're seeing the accuracy and the flop count and so forth. Could you be mentioning the benchmarks that these are running on?
You mean here?
In each of your results tables.
Yeah, these are the data sets. So these are existing pruning approaches.
Yes, but the accuracies are on what workload, what benchmark? ImageNet,
Yeah, ImageNet. Oh, actually, this cannot be.
Okay, thank you.
No, it's not. This is, sorry, this is CFAR. Yes, CFAR 100. Yeah.
Uh-huh.
And
okay, thank you.
Yes, it's not ImageNet. And these these references would be in our paper here. So these are existing works that do filter pruning for a given target. So this is the target here, and this is the accuracy that it's obtained. Is that clear now?
Yes, thank you.
Yeah. So the ranking, the advantage is the ranking is learned once. And then once you have a target, you can, based on the target flop count savings that you want, 50%, 60%, you can identify which filters based on their importance should be pruned, and then the resulting accuracy is likely to give you the best across existing works. One thing that we also noted is the flop count versus the pruned flop count. So the relationship between flop and accuracy is, flop and latency is almost linear. I'm not going to say this as a rule. It's a good rule of thumb, and these are a couple of platforms we tried it on for both ResNet 50 and MobileNet v2. MobileNet v2 is slightly different, but this is good news in terms of, at least in this case, in terms of relying on sort of a proxy comparison between flop complexity and latency. Now, if you'd like to think about what is in between channel pruning and quantization, or how can you think holistically about this, we will need to go back to storage versus accuracy. So fixed and mixed precision, if you remember, the idea is that fixed precision is likely to give you a trade-off between accuracy and storage. On the other hand, mixed precision is likely to push this trade-off curve further to the left, meaning a better trade-off curve. But it comes with quite a bit of overhead. So mixed precision quantization requires hardware software support, right? I mean, your hardware needs to support the mixed precision, but also your software needs to know about that and do or compile the application properly and optimally. To remove some of this, to be able to do apples to apples comparison, we should probably do this in an isomodal size quantization approach. In other words, it's not sufficient to look at the same model with different types of representations of 2-bit or 4-bit quantization, but perhaps look in a pruned down model that uses a different quantization level, but what is common between the two is the storage that they use. So your model size is what counts from I guess a storage perspective. So this is probably a more fair comparison. Different models, perhaps one resulting from pruning the other, but using different quantization levels. And we can see if this is the ISO model approach is what we care about. Is there a winning bitwidth, a single one? Because mixed precision is worse in terms of hardware software support. So just using one might be cheaper and might give us better results. So we wanted to test this hypothesis, and this is the question we asked. So we looked at a few examples, ResNets, VGG, MobileNet v2. So this is different than others because these use regular conv layers, whereas MobileNet v2 relies on separable convolution, depth-wise separable convolution. So what you can see here is the accuracy as a function of log scale size of the model, right? So in the case of ResNets and VGG, the winning bitwidth, which is at the top, highest accuracy, is the 1 bit weight, and activations are all in all cases 4 bits. In the case of MobileNet v2, the winning one is actually 4 bit, but it does seem like we do have a winning bitwidth across all these model sizes. So it's not universally the same, but we wanted to see, what makes MobileNet v2 different? Why is it a 4 bit versus a 1 bit? And it all boils down to the fact that in inverted residual blocks, we have 2 conv with a depth-wise convolution here. So we wanted to see which of these actually introduces this inversion in, from a ResNet to an inverted ResNet, if you want, which pushes the 4-bit weight representation to higher accuracy. So our experiment was to basically identify this block, the depth-wise separable convolution here, and substitute a regular conv layer with this and see when do we see this change or this inversion in, from 1 bit being best to 4 bit being best. So we started with the original one and we started to replace a regular conv layer with this block here. So these are variants ABC. And as you'll see, eventually, moving from the original VGG, variants ABC starting with B actually push the best bitwidth to the 4-bit representation as the best. But already, if you look at variant C, but not quantizing the depth-wise convolution, you can see the original trend still stands. So it appears that quantizing the depth-wise convolution is actually what makes the 4-bit weight representation best in terms of accuracy. So this is something to use when we try to reason which bitwidth is best. If we allow channels to scale, some weight bitwidth is better than others, but the question is which one is it? Our observation is convolutions with higher fan-in, like depth-wise convolution, will allow lower bitwidth to be better and achieve lower quantization error. And this was confirmed on larger datasets like ImageNet. MobileNet v2, again, 4 bits, ResNet 50, 1 bit. And not only that, it's also better than mixed precision at the same model size. So if you look at these, you have mixed bitwidth precision here. The winning one is still the one that we obtain. But also it's confirmed across various expansion ratios. So the result is pretty general. So there is a bitwidth to rule them all. And because it's only one, there's lower hardware software cost. Your hardware only needs to support that and your software as well. So higher convolutional fan-in allows for a lower optimal weight bitwidth. And this single weight bitwidth is able to outperform mixed precision quantization, which we've seen is higher than just single precision, but is expensive. So this is likely to give you a more practical solution. So if we're able to do this, and this concludes my talk, when pushing all of these applications to the edge, the answer to a very simple question like what's my name would actually be very simple. And that's a screenshot of my smartphone, was my smartwatch saying, well, you're Diana, that's what you told me anyway. So it would know how to answer, but it wouldn't have to go to answer that question in the cloud. Thank you. I'm happy to take any questions.
Thank you, Diana. So I'm going to use moderator privilege here and ask you to just go back a few slides to when you're comparing the different bit widths. I think it was slide 42.
Yep.
Yeah. So first of all, we're looking at ImageNet here, or is that right? Or
this is ImageNet, yes.
Yeah. And so you're showing. Well, maybe you could just take it from the top again here.
Yeah.
Because the results seem too good to be true in terms of one bit's always going to be best. So, or sorry, one bit width is always going to be best. So if you could just take me through that. Yeah.
Right. So so this is what this shows here is that for a given model size constraint, the bit width for the weights that gives you best accuracy is 4 bits for MobileNet v2 and 1 bit for ResNet 50. And so if you look here, we start with floating point, 8-bit representation, flexible, and I forget what 29 is. It's a mixed precision approach. And then, but what they all share here is the same model size. And this is the original model size, and this is the target model size.
And Diana, are you retraining here for these different bit widths, or is this post-training quantization?
We are retraining, yes.
Mm-hmm. Okay. All right. Thank you. Well, let me get to the audience questions. So the first one I think is probably one that many people are asking, which is, so you've shown this on computer vision applications. Have you tried audio, biosignals, natural language, any others? That's
a great question. This is what we're trying to do now. So we're pushing this to. In fact, we're trying to come up with a hardware compiler that would allow you to try multiple applications, not just image classification, but we're moving to object detection. And also, ideally, would like to also go to natural language processing and other types. When I say hardware compiler, I mean the results that I showed in the beginning, the hardware results are post-synthesis, and also we demonstrated on FPGA. So what we want to do now is actually where each processing element is a lightweight version of its original full precision. So you're going to be able to customize the number of processing elements, the type of communication, the storage. So hopefully that would give you an idea as to how it would look like in.
Okay, thank you. So we have a good question from Hun Choi here, which I think is relevant to exactly the slide that you're on. So let me jump to that. Isn't the result showing the better result with less bit width due to the gradient solver issue? If gradient solver is perfect, more bits should be the superset of less bits and should show result. Due to the limit of gradient solver, the results are reversed, isn't it? And I would just tack on, maybe it's the gradient solver, maybe it's something else, but the obvious intuition is that more bits should always give you more precision. So maybe you could address that.
In our experience, more bits doesn't necessarily give you better accuracy. I guess it's what we're trying to show here. So what is common across all this is model size, and the way we get to that model size might be different. Might be using mixed precision, might be using a single precision, or might be relying on identifying, what is this model that is a combination of pruned and quantized. So I guess it's not always that more is better, but the way you get to the better might be harder because here it's not quite a fair comparison, except for the fact that it's ISO model size, because you do have more degrees of freedom in identifying which model fits this. if you know what I mean. So typically when you train a model, you start with, okay, this is my model. I'm going to try to find the best set of weights that fit this. Then I'm saying, okay, what is the precision that I'm going to allow these weights to be, and it's either fixed or mixed. If it's mixed, you already do better because you have an additional degree of freedom. But if you also allow your model to be different, your search space, or your design space, I should say, is different. So this is why we're able to push the envelope further, right? So, and this is something that also in neural architecture search is really hard to make comparisons, because there's so many things. You have the different design space or search space, you have a different algorithm, or you have a different way to get to the result. So it seems surprising, but in fact it's not. It's just that we allow more knobs to be changed at the same time. I don't know if that makes sense.
Yeah, it does make sense. So we have a question from Maria Nyamakuru. What's the difference between FLNN, which I think probably means flight NN, performing better than LNN? Let's see. So let's see. I would assume that flight LNN with 4-bit and 2-bit would be better than LightNN with 2-bit, but not better than one with 4-bit, because you can represent the flight neural network weights with the 4-bit. So I think it's kind of similar to the last question, where the whole audience.
Because I was actually going to go here. The flight NN. So the flight NN is actually, in some sense, like I said, is not surprising, because the mixed precision allows you to get to better accuracy. But I guess the question has to do not with this particular one, but with the winning bitwidth work at the end. Is that right?
It seems to me a variant on the question that we're all trying to cope with, the fundamental intuition that you should be able to do better with more bits than less. But I think what you're pointing out here is more flexibility, even with less bits, is better than more bits overall.
Yes.
Yeah. Okay, great. Sabak Kundu asks, is it not counterintuitive to see?
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.